Hey everyone, and welcome. Today we're diving into one of C's most powerful and, let's be honest, sometimes most feared features, dynamic memory allocation. If you've ever been stumped trying to figure out how to handle data when you just don't know its size up front, well, you are in exactly the right place. We're going to pull back the curtain on the heap and give you the keys to managing memory like a pro.
So let's just imagine for a second. You're writing a program. Maybe it needs to process a text file someone gives you, or maybe it needs to handle a list of names that a user is typing in. You've got a big problem, right? You have literally no idea how big that file is or how many names you're going to enter before your program is actually running. So how do you possibly set aside the right amount of memory for that? Well, the most basic way C handles memory is what we call static allocation. But you hit a wall with this approach, and you hit it fast. You see, with static memory, you have to decide on the size of every single variable before the program even runs. It's kind of like trying to pack for a vacation without knowing if you're going to Alaska or Hawaii, or if you'll be gone for a weekend or a month. It just doesn't work for every situation. And this slide, it lays it out perfectly. On the left, you've got static allocation. It's rigid, the size is locked in when you compile your code, and the good news is it's all managed for you automatically on something called the stack. Super simple, but not very flexible. But then, on the right, you have our solution, dynamic allocation. Here, you get to decide the size while the program is actually running, and you manage it yourself in a special place called the heap. This is where the real power is.
Okay, so how do we break through that static wall? Well, we turn to the heap. The heap is the answer to our problem of not knowing data sizes ahead of time. It's this huge, flexible resource that's just sitting there, waiting for your program to use it.
The best way to think about the heap is like a giant self-storage facility. Seriously, your program can walk up to the front desk at any point and say, hey, I need a storage unit that's exactly 500 bytes. Or, you know what, I need a huge one. Give me 10 megabytes. The heap just finds an empty spot and hands you the key. Now, to actually use the storage facility, C gives us a small but really powerful set of tools. These are the specific functions you're going to use to ask for, manage, and eventually return those memory blocks. It's your personal allocation toolkit. And this right here, this is the entire game plan. You have to follow this life cycle every single time. Think of it like a four-step dance. First, you request the memory you need. Then, and this is super important, you always check to make sure you actually got it. Once you know it's yours, you can use it to do whatever you need to do. And finally, the critical last step, you release it back to the system when you're all done. All right, first tool out of the box is malloc. This is your go-to function for asking for memory. It's basically you telling the storage facility manager, I need a unit of exactly this many bytes. In return, they give you a pointer, which is pretty much the address and the key to your brand new block of memory. But here's the catch. That storage unit might have a bunch of junk left over from the last person. The memory is not clean. Next up, we've got calloc. It's a lot like malloc, but with a couple of really key differences. For one, it's designed specifically for arrays, so you tell it how many items you want and the size of each item. But most importantly, calloc cleans out the storage unit for you. It sets every single byte to 0 before it hands you the key. Pretty neat, right? So, which one should you use? This slide really breaks down the trade-off. Malloc is your speed demon. It's fast, it's simple, you just ask for a chunk of bytes. But it's your job to deal with any garbage data that might be inside. Calloc, on the other hand, is a little bit slower, but that's because it takes that extra helpful step of zeroing everything out for you. That makes it safer and way more convenient, especially when you're working with arrays. And now, for what is, without a doubt, the most important function in your entire toolkit, free. Look, when you're done with your storage unit, you can't just walk away and leave the door open. You have to go back to the front desk and return the key. That's exactly what free does. It tells the heap, hey, I'm finished with this memory block. You can give it to someone else now. This brings us to a really crucial point. Having all this control over the heap is an incredible power, for sure, but it absolutely comes with some serious responsibilities. See, unlike static memory that gets cleaned up for you automatically, when you're using dynamic memory, you are the janitor. The cleanup is 100% on you. And if you're not careful, if you don't take that responsibility seriously, you can run into two classic program crashing bugs. The first is what we call a memory leak, and the second is something called a dangling pointer. Let's take a look at what these actually mean. A memory leak. Okay, let's go back to our storage unit. A leak is like you rented the unit, you put all your stuff in it, and then you lost the key and you forgot the address of the facility. That unit is still technically yours, you're still paying for it, but you can never ever access it again or give it back. In your program, this means your available memory just shrinks and shrinks and shrinks until, maybe, it crashes. A dangling pointer. Oh, man. This one is somehow even more dangerous. This is like you properly returned the key to your storage unit, but you kept a copy for yourself. Then the facility rents that same unit out to someone else. If you then use your old copied key to waltz into that unit, you have no idea what you're going to find. You're probably going to cause some serious chaos. You are accessing memory that doesn't belong to you anymore, and that leads to disaster. So how do you avoid these disasters? It's actually pretty simple. You have to live by one single golden rule, and it's right here. For every single time you call malloc or calloc, there must be a matching, corresponding call to free. It's a perfect one-to-one relationship. No excuses, no exceptions. And that, right there, is the grand bargain of dynamic memory. That's the deal. You get the incredible power and flexibility to make your program adapt to any data size while it's running, but in return, you take on the full 100% responsibility of managing that memory's entire life, from creation to destruction. Once you really understand this trade-off, you unlock the ability to build some seriously complex and powerful applications. We're talking about data structures that can grow and shrink as needed, or programs that can handle massive files with no problem at all. The flexibility is now yours. You have the keys to the heap, so the only question left is, what will you build?